Yeah, what I'm going to talk about today is endpoint estimates. It's this project with Odysseas Bacas, Valentina Ciccone, Francesco Di Plinios, Yannis Parissis, and Marco Vitturi about endpoint estimates for Fourier multipliers with Zygmund singularities. Okay. Of course, feel free to stop at any time. I cannot see you, so maybe make noise to stop me if you have questions. And yeah, let's start. Okay, so endpoint estimates. Okay, so the starting point is the most classical object, Hilbert transform, which I've written here both in its form as a convolution operator with the Hilbert kernel and also in its multiplier definition. So defined by the multiplication for the Zygmund function on the Fourier side. Okay. And in this second form, it's particularly easy to see that the Hilbert transform is a bounded operator from L2 to L2 because Zygmund is bounded function. But we also know that the Hilbert transform is bounded in any LP space with P between 1 and infinity. And on the endpoint 1, okay, we are not going to have the L1 estimate, but we have the L1 to weak L1 estimate. In fact, the L2 estimate and the weak L1 can be combined with the Marcinkiewicz interpolation to recover the other LP estimates and duality, self-adjointness. Okay, but if the L2 estimate is easy, let me tell you how to go about the weak 1-1 estimate. And the proof requires the introduction of a powerful tool, the so-called Calderón-Zygmund decomposition. And if you're not familiar with this, the way it works is that we start with a function f, and we want to decompose it into two parts, a good part G and a bad part B, according to an auxiliary level lambda. So the way is that we have our function f in black, we have our level lambda, and then we look for the maximal dyadic intervals on which the function on average is above lambda. Okay, so you see that on I1 and I2, the function is above on average over lambda. And then we define G on these intervals to be constant, the level lambda, and outside of them to just reproduce the function f. And then B is defined just by difference between f and G. Okay? And okay, this is like a decomposition that could look like any other decomposition, but it turns out that it has very nice properties, both for G and for B. For example, G turns out to be controlled both in a L1 sense and in an L infinity sense. In L1 by F and in L infinity by the level, okay? And these two estimates combined provide also a control on the intermediate L2 estimates, L2 norm, in the way that the L2 norm of G to the power 2 is bounded by the L1 norm F and the L infinity norm, lambda. Okay? And then there are also good properties for B that I don't want to go too much into details, but basically B is very well localized to these intervals and it has a cancellative property. Okay, and let's see how to use these two properties in red to recover the weak 1-1 estimate. So of course we want to look at the level set of the Hilbert transform of F. And we can separate, since the Hilbert transform is a linear operator, we can look separately at the superlevel of G and B. And let's work with the superlevel of G. We can use Chebyshev to go to estimate with the L2 norm of a Hilbert transform of G over the level. And now we can apply the simple L2 estimate to HG to control it with L2 norm of G over lambda square. And now we are going to use the control that is provided by Calderón-Zygmund decomposition. so that we have L1 norm of f, lambda over lambda square, and lambda simplify with the square. So we obtain exactly the kind of right-hand side that we want for an L1 to weak L1 estimate, okay? And this is the way to go about the G part. And the way to go about the B part, it relies on the localization and cancellation properties of B, but I would like to focus, I would like you to focus on the G part. Okay, and one last remark before going to the next slide is that the way we have decomposed G, F into G and B is an operation that is happening on the X variable. Okay, so we have looked where f is big, and then we have done some sharp cutoffs. Okay? Okay. So you might wonder whether these boundedness properties are just hold true only for the Hilbert transform or for a more general class of multiplier operators. For example, let's say that you define the operator by taking the Fourier transform of f and multiplying for the function m. What kind of LP estimates you can hope for? And indeed, like the same LP and endpoint estimates that we have for the Hilbert transform can be proved for the more general class of Hörmander-Mihlin multiplier. What are Hörmander-Mihlin multiplier? Okay, so they are multiplier that satisfies a certain smoothness and decay condition that is explained here, that I would like to show you graphically in a second. Okay, you might be familiar with this, otherwise ignore this this formula and look at the picture. So again, this is the signum function, which is the multiplier of the Hilbert transform. You can imagine that you can decompose it into some smooth bump, something like this, where these smooth bumps, they all are associated to dyadic scales. Okay, so you see like this is kind of dyadic scale 1/2, this is dyadic scale 1, 2, and so on. And you see that the further away these smooth bumps are from the origin, the less steep they are. Okay, so you see like this red one close to the origin is very steep. This blue one is less steep. This property is the one that is encapsulated into the Hörmander-Mihlin multiplier condition. And the thing now is that once we have these smooth bumps, we don't need to we don't need them to be precisely the one that decompose the signum. We can multiply each one of them by a bounded coefficient and sum them back again. And the kind of multipliers that you obtain this way are the Hörmander-Mihlin multiplier with respect to the origin. So this smoothness decay condition is with respect to the origin. And the same estimate hold true for this Hörmander-Mihlin multiplier. Basically, a way to see it is that these smooth bumps that we use to create the Hörmander-Mihlin multiplier, if we think of them as a Fourier transform and we look back at the function phi, the function phi is going to be a cancellative bump. And of course, like there is a relation between the scale of phi hat and the scale of phi. So for example, the next psi hat is going to be broader in frequency, but it's going to be narrower in space, in time. Okay, and this red and blue bumps, what is important is that they are cancellative. So in some way, they are kind of atoms of cancellation that interacts well with the Calderón-Zygmund decomposition into good and bad part. Remember the cancellative properties of defining the bad part of the Calderón-Zygmund decomposition. Okay, and in fact, like an even better control than LP estimate. It's known for these Hörmander-Mihlin multipliers in terms of sparse domination. Okay, I'm not going to tell you in details what is sparse domination, but it's a way to control a function or the operator, or rather the form associated with the operator. You see that we have dualized the operator with a function g in terms of a positive form, which is made out of averages of f and g summed over not all dyadic intervals. These calligraphic Ds are the dyadic intervals, but over a subfamily of sparse dyadic intervals, where sparse is the next best thing after disjointness. Okay, so for example, if you look at this collection of intervals, they are not going to be disjoint because we have some overlapping. But at the same time, the overlapping is not too much, in the sense that for every interval, we can find big portions that are separated from the one contained. For example, this interval in the middle, this part on the left is disjoint from the interval above. Okay? And this kind of sparse intervals, again, this concept is closely related to Calderón-Zygmund decomposition in the way that they can be obtained by performing Calderón-Zygmund decomposition at different levels. Okay? Okay. Great. So now you could ask, let's go back to the smooth bumps that we had before to construct the Hörmander-Mihlin multiplier. What if instead of being smooth bump, they were sharp cutoff? So you see, like here on the second picture, I'm just portraying a characteristic function. Okay? And if I sum them, the kind of sum that I obtain is something like this. Okay, you see that the new function m is going to be constant on certain intervals, but it's going to have certain jumps away from the origin. Okay? And you could ask what kind of LP estimates or endpoint estimates I can expect for such a multiplier. Note that, okay, this multiplier is not going to be Hörmander-Mihlin with respect to the origin, but still, it still satisfies some smoothness and decay with respect, no longer just with respect to the origin, but with respect to the collection of dyadic powers, which is the set Xi-Lac, the lacunary set. Okay, so again, we could ask what kind of estimates we expect for multiplier operators that satisfies the Hörmander-Mihlin condition, not with respect to the origin, but with respect to, for example, the lacunary set. Okay. Okay. Okay, this is what I said, that we can imagine of performing the same decomposition that we did before for the Zygmund function, now on each one of these constant intervals. So you see the scale. Of course, now the amount of scale is going to be limited above by the scale of the interval 2 to 4, but okay, the game is similar. And it turns out that Sjogren and Schollin proved that if we have such a Hörmander-Mihlin multiplier with respect to lacunary set of singularities, we can right away upgrade the LP estimates. Obtain LP estimates from the LP estimates of Hörmander-Mihlin multiplier, classical Hörmander-Mihlin multiplier. LP estimates in the open range. So you could ask, maybe we also managed to get the endpoint estimates, weak 1-1 endpoint estimate, but this turned out to be wrong, because Tao and Wright in 2001, they identified the correct endpoint estimate for such Hörmander-Mihlin multiplier that is not L1 to weak L1, but it is L log L square root to weak L1. Okay? And this space L log L is an example of Orlich spaces, but basically, for the moment, it means that you have a function belongs to this space, L log L, 1/2, if this integral is finite. You see, we have f times square root of the logarithm of f, basically, and just the e to make it meaningful, positive quantity. But what I would like to stress is that this quantity on the right is not going to be the norm. The way to define the norm of this Orlich space is more involved and less open to algebraic manipulation, let's say, than the classical LP norms. Okay? And now, of course, you could play the lacunarity game over and over again. So for example, you could look here. You could start with just the point 0 and then produce the lacunary set, that is the dyadic powers, and then add another dyadic decomposition. So basically looking at the numbers of the form 2 to the n plus 2 to the k, where k is strictly smaller than n. And you could iterate this game, producing a tower of lacunary set of different orders. You see, like this 0, 1, and 2 are stand for the order of lacunarity. Okay, so Sjogren and Scholin tells us that the LP estimates all true for any one of these lacunary, for Mihlin-Hörmander with respect to the lacunary set of any order. But again, like the endpoint estimate has to be upgraded now to L log L tau over 2, where tau is the order of lacunarity. And this was proved by Odysseus, Valentina, Yannis, and Marco. Okay? And the underlying property of the lacunary set that allows for such endpoint estimate is the so-called Zygmund inequality for lacunary set, okay, which was proved by Zygmund for the case of lacunary set of order 1, and then Bonamy for lacunary set of any order. And what does this upgrading Zygmund inequality says? It says that if we have a periodic function on the interval 0, 1, and if we look at its Fourier coefficients, but not all of them, just the ones that correspond to lacunary frequencies, then the small L2 sums of this coefficient is going to be bounded by the L log L tau over 2 norm of f of the original function. Okay? And this is an upgrade because in principle, for any set of frequency, the only kind of control that we can do is with the L2 norm of f. This is just Plancherel. And on compact sets 0, 1, we have this inclusion. We have that L2 is contained in any of these spaces L log L, which are all contained in L1. So you see, we obtain, by having this control with the L log L norm of f, we have an upgrade on that is allowed only for lacunary frequencies. Okay? Questions so far? Okay, if not, let me move on now to our result, which is a generalization of this kind of estimate. So what we managed to prove with Odysseus, Valentina, Yannis, Francesco, and Marco is that we can play a similar game for any set of singularity xi. Okay, so let us be given a set Xi, a closed null set. So a subset of this, we are on the line, closed null set on the line. So collection of point. And now we need an auxiliary or Orlich space. I won't go into the definition, but you can think of it as, let's say, the generalization of the L log L spaces. Okay. And now, given Xi and X, suppose that we have a so-called multiscale Zygmund property in the following sense. Take our set Xi, let's start here, Xi, and you rescale it with 2 to the n. And then go to the nearest, closest integer frequencies, okay? And now suppose you can do the same upgrading estimates of before with now summing over this kn set of frequencies and having on the right-hand side the x norm of f. Okay, so before we had x equal to L log L and Xi being the lacunary set. Okay? And now this is called multiscale because we don't want this to hold only for a specific 2 to the n, but for throughout all 2 to the n's. We want this constant z asterisk x Xi to be finite. Okay? Okay, so suppose we are under this condition. Then the kind of endpoint estimates that you can expect for multiplier operators given by functions that are Hörmander-Mihlin with respect to this set of singularities Xi, okay, is from x to equal 1. Okay? And in fact, not only this is the kind of estimates, this is, I mean, not only this is a sufficient condition, but this is also a necessary condition in the sense that this constant in the multiscale Zygmund property, z asterisk x Xi, can be characterized as the best x to L1, weak L1 estimate we have for multiplier operators Tn upon an appropriate renormalization. Okay? And not only that, not only we have the endpoint estimate, but we also have a sharp sparse domination of the form associated with the operator, where now, okay, we have the z asterisk constant popping out, and now the averages that appear in the sparse domination, they're not L1 averages, but they're going to be averages in the norm X. Okay, of course, otherwise we would have obtain better endpoint estimates. Okay, and the normalization is just in terms of the Hörmander-Mihlin condition that I already told you about. So, okay, we have a set of frequency Xi that is going to be where we might have jumps, but outside of them, the function m is smooth and decays appropriately. Okay, so this is our result. And in the remaining part of the talk, I would like to go a bit through some aspects of the proof, and in some way trying to draw some parallel with the Calderón-Zygmund decomposition that we have seen. So are there questions?
Can you say a bit more about motivation for this Zygmund property?
What do you mean? Like, okay, this is it turns out to be exactly the underlying phenomena that dictates the endpoint estimates. So let's say if you're trying to understand what is the endpoint estimates that you can expect, this is going to be exactly the same problem a posteriori as trying to understand the multiscale Zygmund property of the set of singularities. And let me tell you that there are examples, okay, like some examples of such multiscale. Of course, like any set Xi is going to have the L2 Xi multiscale Zygmund property because of Plancherel. But then also we have seen the example of lacunary sets with the L log L kind of spaces. But you can also build sets Xi that are not the union of lacunary sets, but they still satisfy some meaningful multiscale Zygmund properties. Okay, so there is a...
Sorry. What I really meant is, why should we be interested in these multiplier classes?
Okay, well, that's a good question, but yeah, I'd say that this is more like, yeah, I cannot provide you an example of like of such a multiplier appearing in other context. But it's more like, the way I think about it's more like a characterization type of result. Yes. But okay, like the thing to conclude is that there are examples beyond the lacunary sets also with meaningful Zygmund properties that are, yeah. Okay, maybe let me think later. But okay, so okay, let's go a bit into certain steps of the proof. Okay, so the first one, so okay, now in the following couple of slides, you will see that we are going to perform through decomposition, one of the operator and one of the function. Okay, and then we are going to try to define an appropriate Calderón-Zygmund decomposition that in some way allows us to play, to make the two decomposition play with each other. Okay, and the decomposition for the on the side of the operator goes through the so-called, or what you could call a phase plane tiling representation. Okay, so the idea is that thanks to the smoothness and decay of our multiplier that comes from the Hörmander-Mihlin condition, you can control the operator Tm in terms of phase plane tiling operators, which are operators defined like this, where you have your function, you are pairing with phi p, and then multiplying with a psi p, and summing over tiles. What are these tiles? Okay, so the idea is that you look at the phase plane, so the plane with variables, with the time variable x and the frequency variable psi, and you highlight, let's say, the singular frequencies, capital Xi. Then you perform a Whitney decomposition of the remaining intervals, and you construct tiles out of this. So tiles are rectangles in this plane of area 1, such that their frequency interval, their vertical interval is 1 appearing in this Whitney decomposition, and the interval in time, it's dictated by the scale. Okay, so the idea is that you tile the plane with such tiles, and then to each one of them, you are going to have wave packets associated to it, which are functions that on frequency, they are supported on this interval, vertical one, like honestly supported on this interval. And in space, in time, they are, okay, morally approximately supported on this interval IP. Okay. Okay. So from now on, we are going to look at this kind of operators, T peak psi of F, defined in this way. This is a standard kind of decomposition in time frequency, on the time frequency plane. Okay. And the next is the decomposition of the function, which is going to go again through certain tiles, but now the tiles are going to have a fixed scale. So you see, like here on the left, we have tiles that are wide and short, and narrower and taller. But here, all the tiles have the same shape because we have fixed the scale. And through this tiling, we reproduce the function through a so-called Gabor representation, because Gabor means that the scale is fixed. Okay. And now this is, let's see how we are going to define the Calderón-Zygmund decomposition, quote unquote. So our G is going to, I call it G because it's going to play a similar role to the one that we had in Calderón-Zygmund decomposition. And it goes like this. Okay, so we can guarantee that we have a support condition on F. So let's say that this is a technical thing that comes out of the in the sparse domination algorithm, let's say. So suppose that your function is supported on a specific dyadic interval L, which has a certain scale, 2 to the n. Okay. Now what we are going to do is that we are going to look at the set of singularities psi. We are going to rescale it according to the scale of L. And then we are going to consider the summands of this earlier, the Gabor representation of the function, not all of them, but only the ones that corresponds to K that belongs to this specific set of modulation. Okay, so you see, like, G is just obtained from the same coefficient of the Gabor representation of F, but just taking some of them. And the ones that we take corresponds to the tiles, for example, in red in the picture. So you see, like, we are not taking all the tiles, just the one in red. And again, this G function is going to have certain properties, which I described here on the left, and here on the right, I recall the similar properties of Calderón-Zygmund decomposition. Okay, so let's look at the first one. The first one tells us that the L2 norm of the function G that we have created is going to be controlled by averages of F through the X norm. And okay, here we have where the multiscale Zygmund property comes in. Okay, and this kind of control for the L2 norm of G, you should compare it with the L2 control that we had before on G in terms of lambda level and the L1 norm of F. So if you take this square and you put it here, you obtain square root of the L1 norm of F and square root of lambda, which you can maybe see as similar to the term here. Okay. And the second property is a cancellation property. So we have that F minus G, which is going to be the bad part in our sense, when paired with appropriate function is going to be 0. Okay, let's ignore the kind of tiles that are this property holds true for, but let's say the nature of this property is about cancellation, which is similar to the cancellation property of the bad part of the Calderón-Zygmund decomposition. Okay. And yeah, these are the tools, the nice properties of the, let's say, Calderón-Zygmund good part. And okay, let me tell you, like, here I'm recalling them. You see the L2 control on G and the cancellation property. And let me tell you what kind of upgrade that they allow us to obtain. Okay, so we have our set of tile P xi, P of xi. And we look at the tiles that are contained with time interval in 0, 1. So for example, you see like before we had all the tiles, all these tiles on the left, but now I'm restricting to those that have spatial intervals contained between 0 and 1. So you see already that it's the area shaded in blue. It's not the full area of before. So we already have restricted our amount of tiles. And next thing is that suppose that we have a subinterval of 0, 1, so such an L, and we are going to further restrict the collection of tiles to those that are not contained in the band associated with 3 times L. Okay, so we had our original L, we enlarge it a bit, and we throw away the tiles that are contained, fully contained in the 3L band. Okay, so we have now P xi and P. So you're going to see that, so there is an intrinsic L2 estimate that is available for phase plane tiling operators, T, P, xi of F, because these tiles are disjoint, and so they interact well with L2 orthogonality, either in time or in the frequency variable. Okay. What I'm going to tell you is that if we further know that our function is supported on L, and we restrict ourselves not to the full tiles P xi, but only to the tiles P, the L2 estimate can be upgraded in the way that we are going to control the L2 norm of the tile operator TPF with now an average of F in the sense of X, the Orlich space X. So this is the maximal function measured in terms of averages in X, in the X Orlich space. Okay? Where again, like on compact, the idea is that on compact subsets, on compact intervals, the space X is going to be is going to contain L2, but it's going to be contained in L1. So it's going to be something in between. Okay, and this is like the main ingredient, kind of this upgraded local estimate is the main ingredient to run then the sparse domination algorithm through the different levels of intervals. Okay, so once again, with this upgraded estimates, I'm here recalling the results that we proved that the kind of for a multiplier that satisfies Hörmander-Mihlin condition with respect to the set of singularity xi. The endpoint estimates is the best endpoint estimates that you can expect is intrinsically equivalent to the kind of multiscale Zygmund property that you have for xi. Okay, where you have x. And okay, yeah, this is the, I'm just recalling the definition of multiscale Zygmund property. And again, okay, what I told you about was about Hörmander-Mihlin multiplier, but you can also do the same kind of estimates for square functions, both sharp cutoff square function or smooth cutoff square functions. Okay, let me not go into details. Or even for Marcinkiewicz multiplier, which are multiplier that are defined by, instead of this smoothness and decay condition, by a bounded variation kind of condition. So the class of Marcinkiewicz multiplier is richer than Hörmander-Mihlin multiplier. And this corresponds, this has an effect in the fact that you have to slightly update the multiscale Zygmund constant, but okay, not in a very non-surprising way. I mean, a very reasonable way. And the last thing is that, of course, like for these operators, or Hörmander-Mihlin square function, Marcinkiewicz multiplier, you can obtain LP estimates, but also sparse domination, which, as always, it comes also with certain weighted estimates. And that's pretty much everything I wanted to say. So thank you very much.